So what can I learn about a function from its derivatives? All right. Because the majority of people in the world are right-handed, a line going that way, as we travel from left to right, is increasing. And that one's decreasing. Yeah. But wait a minute. If this line is increasing, what do I know about the slope of this line? Positive. Similarly, on this side, that slope is negative. So let's take this exact same idea and generalize to things other than lines. If I'm looking at a derivative, that's a slope. Well, it's the slope of the corresponding tangent line. So if I have a section of the graph where my derivative is positive, I'm going to say that section of the graph is increasing. If I have a section of the graph where my derivative is negative, I'm going to say that section of the graph is decreasing. So if I have an interval, and on that interval my derivative is positive, then my function is increasing there. By the way, swap that to negative, you swap this word to decreasing. So just as I talk about a line that goes up or down as we go from left to right, I can now talk about a curve that goes up or down in the same fashion. How do I find the appropriate pieces of the graph that will do these things? Let me start with what I hope is a simple example. And I picked this one because you already know the shape of this graph. What is the shape of this graph? This is my parabola. And this one opens upward. Now think about walking across this curve going from left to right. The left side is coming down. The right side is going up. I just need to know where it changes. But if the graph looks like this, I've got a critical point. And that critical point should be a minimum. If I already know what the graph looks like, oh, there's a minimum there. Great. As I go from left to right, I have a part that's decreasing, I have a minimum, I have a part that's increasing. Fermat. What does my buddy Fermat tell me about that minimum? What's Fermat's theorem say?
If there's a local strain at x equals c, then the derivative is equal to zero.
The derivative is zero there. So I can find this spot by telling me where the derivative is zero. And that means that everywhere else, the derivative is either positive or negative, right? So I know that if I take the derivative here, and I set that equal to zero, I found my critical number, critical value. Having that critical number means I know that everywhere else, the derivative is not zero. So let's make a number line. That's the spot where my derivative is zero. That's the only spot where my derivative is zero. Everywhere else, it's something. It's either positive or negative. I need you to give me a number that is less than 5 halves. Any number less than 5 halves. 1. I'm going to put that number over here. I'm going to put it in a little box. I'll deal with that in a second. Let's do the same thing on the other side. Give me a number that's bigger than 5 over 2. 3. Whatever happens to my derivative on the left side of 5 halves is the same for any number you plug in. Because if my function is continuous, the only way it changes from negative to positive or positive to negative is to go through 0. And the only place we have a 0 is here. So whether you're going to get a plus or a minus over here, doesn't matter which number you plug in, any number will do. So if I take 1 and I plug it in to f prime of x, 2 times 1 minus 5 is negative 3. I don't care that it's negative 3, I just care that it's negative. Now notice, if you'd pick 0, you'd get negative 5. If you pick 2, you'd get negative 1. If you pick negative 16, you'd get negative 37. But no matter what number you pick, as long as it is smaller than 5 over 2, you're going to get a negative answer. What happens when I put in 3? Two times 3 is 6. 6 minus 5 is positive 1. I just care that it's positive. And that means that in this entire section of the graph, my function is decreasing. And in this entire section of the graph, the function is increasing. And that matched our intuitive picture, didn't it? Our parabola had a minimum, so we'd be down then up as we go from left to right. Down then up. Well, now I found the intervals AB. This function is decreasing everywhere less than 5 over 2. And it's increasing on the other side. So I found the interval of increase and the interval of decrease. This is referred to as a sign chart. Or a sign diagram. And it is, to me, the critical method for analyzing where I'm going up and where I'm going down. Questions? Yes, ma'am.
So one of the point is. And do that, and then it's 500 feet of the original function.
Exactly. The derivative is telling me about the behavior of f. That's my advantage. I can learn about what f is going to do by looking at f prime. Now, this is particularly useful to me if I think about more complicated functions. Well, this is worse. All right, wait a minute. I learned a bit about the general shape of functions in algebra. This is a fourth power. I know the end behavior of an even power. Squares and fourth powers and sixth powers and eighth powers. If it's an even power, the ends go the same way. They either both go up or they both go down. And what tells me whether they're up or down is the number in front of the highest power. That tells me the right end is up because it's positive, so the left hand must be up. But what happens in the middle? There should be this wiggling back and forth, right? If there's all that wiggling back and forth, I'm going to have some increase and decrease and increase and decrease and weird going on, right? But now, using f prime, I can tell you exactly where that happens. So let's take our derivative here and do this process again. This is my problem. In this case, I don't have a good picture. I know the graph is going to go this way and this way, but in the middle, it's going to do all this weird stuff. Let's figure out what it's doing where. What is f prime? Hang on a sec. What happens with that one? Aha. Good catch. Hey, wait a minute. I'm going to do the same thing. I want to find my critical numbers. The critical numbers are where this is equal to 0. Okay, well, here's where my algebra skills need to come into play. This one tight. If I want to set that equal to 0, I got to factor that. Fortunately for me, what do I know about all the coefficients? They had, well, the variables have an x. What about the coefficients? They all have a 12. So I can take a 12 and an x out of that. What's left behind? And that, again, I can factor that. That's a quadratic. If I can't factor it, I could use the quadratic formula, right? But in this case, I can factor it. I want a -2, so I'm going to use 2 and 1. I want it to be negative. I want them to add up to -1, -2 plus 1. And that means this has 3 critical numbers where each of these pieces is 0. So I have 3 critical numbers. I need a sign chart again to figure out what's happening. I'm going to make a number line, put those numbers on it. In order. Then I need those numbers in the boxes, the numbers I was going to test. So I need a number smaller than -1. Any number will do. A number between -1 and 0. A number between 0 and 2. And a number bigger than 2. Now here's the problem part. I need to plug that into f prime. But f prime is ugly. But I took f prime apart. I factored it. So what if instead of plugging into this version of f prime, I plug into this version of f prime? I'm going to do that by plugging into each piece separately. Over here, I'm going to make a row for the first piece, a row for the second piece, and a row. I started to say the third piece, so I wrote down a 3. Don't do that. Write down the correct number, 1. Each of these gets their own row. Each of the number marks on my number line separate the columns. Does that make sense? Well, now I can just plug these numbers into this, and that's a lot easier to plug into. -2 times 12 is negative. -1/2 times 12 is negative. I don't care what the number is. I just care what its sign is. 1 times 12, 4 times 12. Those are both positive. Please notice that only changed once across that whole line from negative to positive because it's 12x. 12x is a line. I like that. That helps. -2 minus 2. -1/2 minus 2, 1 minus 2, 4 minus 2. Same thing with the +1. Now, how does this get me f prime? Well, f prime comes from multiplying all those pieces together. So I'm going to multiply down each column. Negative times negative times negative. If you multiply 3 negatives, is the result negative or positive? The whole thing will be negative, and that means we're going down there. Here I have 2 negatives. 2 negatives make a positive. Here I only have 1. Here I have 3. There are my wiggles back and forth, aren't there? 1, 2, 3, 4. I made some sort of W shape. And that matches my intuition up here. I have my original function, right, Jordan? My original function is decreasing here. That's everywhere from negative infinity all the way up to the line. And also this section. That little funny symbol between those two intervals, that's an or symbol. So I can be in this one and decrease. I can be in this one and decrease. I can be in either of them, this one or that one. We're going to use that or. And it's increasing between -1 and 0. Or I can be in this part from 2 off to infinity. A common mistake made here. You'll notice the numbers that are on these intervals are my critical numbers, not the testing numbers, the critical numbers. Some people will say, oh, I went to -2, so I'll use -2 here. It goes all the way up to the line. Make sense? Talk to me. Questions? Some of you are looking at me like, What's happening on this graph when x is equal to 2? If I only looked in a little neighborhood around x equals 2, what would I see in the picture? That's telling me about the extremes that's going on there, right? Hey, think about Fermat's theorem. I have a place where my derivative is 0, and I have it going down and coming back up. What has to be happening here? A local minimum. What has to be happening here? I just figured out a way to test my critical numbers to tell me whether or not I have a maximum, a minimum, or something else going on. I can use this chart. If there should be a big if at the beginning of this that says, if my derivative exists, right? If I have f prime at this point around C, and I go from being positive to being negative, then I had to be going up, coming down, there's got to be a maximum there. If I go from negative to positive, I'm going down and then up, there has to be a minimum there. If it doesn't change sign, I have a flat spot. We've seen that before, right? Remember our x cubed picture? We just flattened out and then kept going up. Ooh. I like this because now if I go back and plug in the actual values of my critical points, I can figure out what the maximum and minimum value of this graph is. I can then figure out if I've got absolute minimums and absolute maximums. Okay, so I need to plug into the original function. So I got to scroll all the way back up here. There's my original function. Let's plug in to that function. Well, plugging in one of those numbers is really easy. If I plug in 0, what do I get? That was a piece of cake. Plug in -1. -1 to the fourth is positive, so I get 3 minus -1 to the third is negative, minus -4 becomes +4. 12 times -1 squared, that's going to be positive. So that'll be -12 and then +5. So what's that? 7. Oh, that's 0. And then when I plug in 2, 2 to the fourth is 16. 16 times 3 is 48. 2 to the third is 8. 8 times 4 is 32. Minus 12 times 4. 2 squared is 4. Plus 5. 48 minus 32 minus 24 plus 5. What do I get?
-12 times 4.
Oh, yeah, well, that makes me wrong there. 48. I feel better. -27. Hey, think about the shape of this graph. The shape of this graph, as I go from left to right, this side is coming down, then we go down to 0, we go back up to 5, we go down to -27, then we go back up. Do I have an absolute maximum on this graph? Because this side's going to keep going up. Do I have an absolute minimum? And the minimum value is -27. That's the lowest spot on this graph. The graph kind of looks like that. Questions? That's a really crappy picture. But you have a graphing device in front of you, so you should be able to graph this much prettier than I did, right? Please do that. Graph this. There's my original equation. Now, since I know the picture roughly looks like this, I know my window on my calculator should go at least as low as -27. I'm going to go down to -35. And if I'm going to do that, I'm going to make my scale appropriate so I can see some of the top part of the graph. I get this picture. I'm going from -35 to 20-ish. I'm only going from like -4 to 4, 5, left, right, so I can see everything. The picture I drew is all straight lines. The picture the graphing device drew is not straight. It curves. But clearly that curve changes. As I go from left to right, the way in which the graph is decreasing or increasing is itself changing. Increase and decrease are told to me by f prime. If increasing and decreasing are changing, what's going to tell me about that? My first derivative tells me how the graph is changing, whether it's increasing or decreasing. If I want to talk about how that thing is changing, I need to look at its derivative. That's f prime prime. That's the second derivative. So let me think about this for a minute. Let's think about f double prime being positive. That means that f prime is increasing. The derivative of this tells me whether it's increasing or decreasing. If my derivative is increasing, that's the slope of a tangent line. If my slope gets bigger, what happens to my line? More vertical. If it was going up to begin with, it'll be going up more, right? What if it was going down to begin with? What if I have a negative slope and it, quote, gets bigger? Gets bigger means it should get less negative. So if I have a negative slope, then I will have a less negative slope, right? Now, if these are points on my curve, and those are the tangent lines, then when I connect these two dots, hey, wait a second, I'm a crappy artist, but there we go. Same thing here. I get a curve. And if I picture this curve all the way across, then it would look something like that, right? That's a cup. It holds water. The concave versus convex, the part that holds, is up. If my slope, on the other hand, if my second derivative is negative, then f prime is decreasing. If I have a positive slope to begin with, what's going to happen at the next dot? What's the line going to look like here? My tangent line. I don't know if it's going to go all the way down, but the slope that is positive is going to get less positive, right? It might actually turn all the way over. Yes? If it was negative, then when I get to the next dot, it's going to be more negative. And so I'll have that sort of behavior. If I continued that all the way through, then my concave side is down. I'm going to use those descriptors. If I have a section in my graph where the second derivative is positive, I'll call the graph concave up. Now notice this, Jordan, I'm gonna really mess with you this time. F double prime is now telling me about F. This is a description of F. This was my description of F prime. So the first derivative tells me about the original function. So does the second derivative. It tells me how it curves. What happens if my second derivative is 0? I'm even flat, right? Like I was with the first derivative, I have a flat spot. I don't actually have any curving going on there. I have a section where the graph is perfectly flat. I have been using the following little symbol to help me remember this for almost 45 years now. If my second derivative is positive, my second derivative is positive. I'm glad he's awake. My second derivative is positive, I'm concave up. If my second derivative is negative, I'm concave down. I get a smile and a frown. I learned that way long ago. By the way, if your second derivative is 0, you're flat. Those stupid little smiley faces have been stuck in my head for decades. If f of x changes concavity at some point from up to down or vice versa, then that point is called a point of inflection. The word inflection means stress. We talk about this in grammar and in speech when we talk about the right emphasis in a word. You got to put the accent on the right syllable, right? Grab a piece of paper. If you've got a loose sheet of paper, this works really well. Take both ends, push one down and one up. And you'll notice you get this sort of squiggle here in the middle, right? Make yourself what looks like a sine curve. The most physical stress, all of you engineers, stress behavior happens right there in the middle where we change from being concave down to being concave up. That's our stress point. That's the inflection of our curve. Hey, wait a minute. Wait a minute. Curviness. I'm going down, then up, I got a curve. I'm going up, then down, I got a curve. I'm going down, then up, I got a curve. I should have inflection points on this graph. That's that function. Let's find them. We already worked out the first derivative. So now I need the second derivative. What's my second derivative? Oh, hang on a second. The potential points of inflection are where this is going to change from being positive to being negative to being positive, right? In order to go from positive to negative, what do you have to do? I got to go through 0. I need to set that equal to 0 and solve it. I see a lot of people abbreviate points of inflection as POI. That's perfectly fine. I'm also going to just shorten it as inflection points. But if I want to figure out where they're going to be, I need to set that equal to 0. Well, that's disgusting. I can at least factor out a 12, right? I have good news and I have bad news. The good news is it's just a quadratic. The bad news is it doesn't factor. Since it doesn't factor, how do I set it equal to 0 and solve? The quadratic formula. X is equal to negative b plus or minus the square root of, that's the only way to remember the damn thing, right? So that's 2 plus or minus the square root of 16 plus 12 times 2 is 24. 24. Over 6. Which is going to give me 2 plus or minus the square root of 40. Oh, no. Negative 2 squared is 4. I squared it twice. 2 plus 28 over 6. If you want, you can turn those into a couple decimals for me. That's fine. When I do that, I get 1.22 or negative 0.55. And that makes sense in light of my graph. One of those changes happens here. There's the negative 0.55. And the other one happens down here somewhere around 1.22. There's my stress between being concave down on the left and up on the right. Questions? A potential complication. What's my derivative? Say again? What's my second derivative? Okay. Interesting point. This function's perfectly fine at 0. This function is defined everywhere. So is this. This one's undefined at 0. I didn't do something in this example. I probably should have. I should have made a chart. If I made a chart for the first derivative, I should have made a chart for the second derivative. If I look at this, 4/3 x to the 1/3 is equal to 0 only when x is equal to 0. So I would make a sign chart. It would look like that, right? Pick a number smaller, a number bigger. put them in. I know what's going on. But when I go to do the second derivative, oh crap. Remember that negative power means that goes in the bottom. And a fraction is only equal to 0 where the top is 0. I don't have any places where my derivative is 0. What other things do I need to look for in a critical point? A value x equals c is a critical number if the derivative is 0 or Chapter 4, Section 1, this is right before Fermat's theorem. My derivative can either be equal to 0 or it can two different options there. Not exist. This function's not equal to 0 at 0, but this function does not exist at 0. So when I go to make my chart for the second derivative, I want to put 0 on there, but I want to make sure I remember that it's a place where my derivative doesn't exist. I'm going to use a dotted line. Some people actually put a little open circle here. Some people write U for undefined at the bottom of that. Then I can do that, and it will help me to remember something different is going on here. I need to know if my concavity changes from one to the other here. If I put -1 or 1 into this, in both cases, it's positive. I don't have an inflection point here. I didn't change concavity. If I actually look at the graph, decreasing followed by increasing, that matches that, but it's concave up on both sides. There's no change in concavity. There's no actual inflection point here. I do, on the other hand, have something interesting. I have a place where my tangent line is horizontal. And I'm concave up. If I put those two things together, I know my tangent line is at the bottom. I must have a minimum. If I'm concave down and I have a spot where my tangent line is 0, I must have a maximum. I can use the second derivative to tell minimums from maximums as well as the first derivative. So there is an additional test for maximums called the second derivative test. If f prime of c equals 0 and f double prime of c is positive, then x equals c is a minimum. There's my picture right there. If I replace this with negative, then I get a maximum. I need to know what's going on to try and get better pictures. I need to understand more about what's happening in my graphs. I need to know what happens on the ends. I need to know what happens in the middle. I need to know what happens at all the turns. And then I'll be able to use my technology to get a good picture. I like drawing on my calculator. It's a lot easier than drawing by hand. But If I don't know where to look on my calculator, I'm in trouble. We'll talk about that more next week. We'll see you all then.